Hello, my name is Noah, and I'll start a presentation on the algebra behind the Floyd-Warshall algorithm and generally how graph algorithms are connected to abstract algebra as a whole. This is an algorithm that allows us to find all the shortest paths between all pairs of vertices in a graph. What actually defines a graph will be outlined later in the presentation. We will use molecular structures, specifically of water, to demonstrate the Floyd-Warshall algorithm, and why we use this specific algorithm as opposed to more famous graph algorithms like Dijkstra's. We will also build towards the intuition and knowledge to be able to understand what it means that this algorithm naturally operates over the min plus semiring. This naturally brings up an important question as to why should we even care about this topic and what is the motivation behind this presentation, and that being navigation apps and maps as a whole, which allow us to see what is the cheapest or fastest way to get from point A to point B, a problem that shows up in everyday life. This shortest path algorithm can be used to solve this exact problem as well as the distances between atoms in a molecule, as these problems algebraically are very similar to one another. An important part of understanding both the problem and the intuition behind the algorithm is getting a basic visual understanding and overview of what's going to be covered during the presentation, which is given by the following video. First, we represent the water molecule, as a graph. Then we build the bond adjacency matrix. After, we then initialize the distance matrix for this graph, and then update our distance matrix using oxygen as the intermediate atom. This allows us to go over the actual connection to algebra behind this update. And lastly, how we can express the entire loop as algebra operations. An unweighted graph is simply a set of points called vertices and the edges that connect them. Looking at our example for the Floyd-Warshall algorithm, if we ignore the numbers for a moment, our graph is defined by vertices A, B, C, and D. The edges are the connections between them: A to B, A to D, B to D, B to C, and C to D. A weighted graph takes us a step further by assigning a value, length, or weight to each of these edges. For instance, in our example, the weight tells us that vertex A is 2 units away from vertex B, and B is 1 unit away from vertex C. So Floyd-Warshall, when given a weighted graph, will output a matrix where an entry in the ith row and jth column corresponds to the shortest distance between vertex I and j. For example, using vertex A, or 1, and vertex D, or 4, we see that the minimum distance is 4, which is a path going through B. While using Dijkstra's, the input is the same weighted graph with an additional starting node, and outputs only the distances from the starting node. We can think of Dijkstra's as the outputting exactly of one row of Floyd-Warshall's matrix output. This then gives us a reason to use Floyd-Warshall, as it gives us information about the graph as a whole, while Dijkstra's only gives us information about one vertex. Using this newfound information about graphs, we can model molecules as a graph where each atom is a vertex and each chemical bond is an undirected edge. Using a molecular data approach, we can use atom positions and atomic radii to decide whether two atoms are close enough to be bonded. This is done through the bond inference rule, which we can see on the left side. It gives us the actual mathematical criteria for when two atoms are actually close enough to form a bond, allowing us to build an accurate molecule-to-graph representation. From this graph, we can construct an adjacency matrix. This is similar to the matrix we talked about earlier with Floyd-Warshall, but instead of representing the shortest paths between A and D, it represents direct connections. We set an entry to 1 if vertex I is directly connected to vertex J, and 0 otherwise. So in our H2O example, on the right, the entry comparing H1 and 0 has a value of 1 because they are connected by a bond. However, H1 and H2 have a value of 0 because they do not share a direct edge. Notice also that because these are undirected edges, our matrix is perfectly symmetrical about the diagonal. Continuing the same example from last slide, water gives us a simple graph with 3 vertices, H1, O, and H2, who only have edges from each hydrogen to the oxygen atom. Therefore, our adjacency matrix only shows local bonds, but does not yet show the indirect hydrogen-to-hydrogen connection. The 0 between H1 and H2 has no bearing on whether two atoms are actually connected or are part of the same molecule. The actual Floyd-Warshall algorithm discovers the indirect separation. To let the algorithm find this indirect separation, we first have to translate our molecule and our adjacency matrix into a slightly different form. We begin by initializing diagonal entries in the matrix to 0, as that measures the distance between an atom and itself. Now similarly, if two vertices are directly connected, we set the value in this matrix to 1. If there is no value initialized at this point, we then set the entry to infinite. This value then represents that we do not know if a path exists, not that one absolutely doesn't exist. So for our H2O molecule, we set 0 for the 3 diagonal entries, a 1 for each hydrogen and oxygen pair, and then infinite for the hydrogen to hydrogen entries. Our next step in the algorithm is to do an update step that adjusts the matrix we just initialized. We want the algorithm to find that indirect connection we talked about earlier. To determine the distance from the first hydrogen to the second, the algorithm considers the oxygen atom as an intermediate vertex. By checking this detour, it finds the root H1 to oxygen and oxygen to H2 has a length of 1 plus 1, which equals 2. Since 2 beats the current value of infinity, is less than infinity, the matrix updates both of these hydrogen to hydrogen entries to 2, finally revealing the true distance. Now imagine doing this for a much larger molecule or network. The full Floyd-Warshall algorithm repeats this exact same comparison for every possible intermediate vertex, which we call K, and every ordered pair of vertices I and J. At each step, it asks a simple question. Do we keep the current path or replace it with a new route passing through K? Because it checks this using the 3 nested loops over n vertices, the overall runtime of the algorithm will then be O of n cubed.
The 4-item chain here shows how longer paths emerge gradually throughout the algorithm. Once B is allowed as an intermediate vertex, the algorithm discovers that A and C are 2 edges apart, and after C is allowed, it discovers that A and D are 3 edges apart, eventually filling up the entire distance matrix. And another simple Dijkstra example is as follows. So starting from S, Dijkstra repeatedly visits the unvisited vertex with the smallest center of distance. It first reaches B with distance of 1, and then he proves distance to A from 4 to 3 through the vertex B. And finally, it reaches C with a distance 4 through B and A. And this illustrates how Dijkstra solves a problem from one chosen source. Now, comparing Dijkstra and the Floyd-Warshall, which are the 2 popular distance calculating algorithms, Dijkstra is usually preferable when we only need distances from one source, particularly in a sparse graph with non-negative weights. Well, on the other hand, Floyd-Warshall computes all source to target distances at once and can handle negative edges as long as there is no negative cycle. And Floyd-Warshall is especially relevant here because its matrix update has a direct algebraic interpretation. So, in the min plus semi-ring, the operation, which is this one, is minimum, and the operation, which is this one, is ordinary addition. Minimum represents choosing between alternative passes, and addition represents joining consecutive paths segments. And for the identity, infinity is the identity for path choice, and 0 is the identity for path composition. So the semi-ring law justifies combining paths consistently. Associativity of the min operation allows many alternatives or many path segments to be grouped in any order. And distributivity shows that extending competing paths by the same segment preserves the comparison between them. And on the other hand, if we replace the min plus operation with simply the Boolean or and end, changes the output of this algorithm from shortest distance to reachability while preserving the algorithm's basic loop structure. So the correctness is proved by invariant. The invariant states that after iteration k, each matrix entry contains the shortest path whose intermediate vertices come only from the first k vertices. The base case records only self-distances and direct edges. And during the induction step, an optimal path either avoids k or passes through k. And the recurrence compares exactly these 2 possibilities. So after k equals to n, every vertex is allowed. So the matrix contains all unrestricted shortest path distances. The main takeaway of this algorithm is that we can model molecular structures as graphs. And Floyd-Warshall algorithm calculates the minimum number of bounds separating every pair of atoms by updating a matrix. And this updating rule is not arbitrary. We have minimum chooses the better path, and addition joins path segments. And in comparison to Floyd-Warshall, Dijkstra solves a related one-source problem, and is a slightly different algorithm. And if you want to know more about these 2 algorithms, the following sources will be a great help, including a video demonstration of the algorithm and some articles, and even the original paper posted by Dijkstra. All right. Thank you for watching.